In this video, I'll show you how to construct interval estimates for a quantitative variable. When you visit your local ice cream shop, you like to get 1 scoop of chocolate ice cream. The scoops seem pretty large to you, and you wonder, what is the average weight of all scoops at the shop? You weigh your scoop. With the help of your friends, you order 27 more scoops of ice cream and weigh them. You compute the average weight of the scoops and get 4.6 ounces. Now, this doesn't quite answer the question. The issue, of course, is that there is some variation from scoop to scoop, which causes variation from sample to sample. So if you ordered another 28 scoops, you'd probably get a different average. So we need a method that will help us understand this sampling variation. Let's start by identifying the population and parameter. In this case, the population is all scoops of ice cream from the shop, and the parameter is the mean weight of those scoops. Then there are numerous hypotheses we can make about the parameter. We could hypothesize that the mean weight is 4 ounces, or that it is 3 ounces, or 3.5 ounces, or any value. And then we want to know which hypothesis is an observed statistic of 4.6 ounces evidence against. Let's start by hypothesizing that the mean weight is 3.5 ounces. So how can we make a model for this hypothesis? Pause the video and think about how you might do this. One idea is to use a model where all of the entries are 3.5. This certainly has a mean weight of 3.5. However, if we sampled from this list, there would be no variation. We would never get any mean other than exactly 3.5. But there is certainly variation within the population of all scoops, so we need to come up with a model that more accurately reflects the population. What we can do is start by using the observed data as a model for the population. We know that the data we observed has a mean of 4.6 ounces. So to make it have a mean of 3.5 ounces, we'd need to subtract 1.1 from each data point to get a model that has a mean of 3.5. The key idea here is that our original data accurately captured the amount of variation in the population. So this model will, too. Then we'll simulate repeating the study many times, each time sampling with replacement. Let's try this out. So here's the model, and we'll set the sample size to 28. And each time we repeat the sample, we'll get a different mean. And after having simulated 1,000 sets of 28 scoops, we can look at a distribution of the simulated sample means. Here is a dot plot showing the distribution of mean weights. So for example, this orange dot represents one 28 scoop sample that had a mean of 4 ounces. And this is all assuming that the mean weight of all scoops is 3.5 ounces. Now what we need to do is find the probability of getting the observed statistic. The observed statistic was 4.6, which doesn't even appear in this distribution, which means that a parameter of 3.5 ounces would not have produced a statistic of 4.6 ounces. Let's try another hypothesis. How about we try a mean weight of 4.0 ounces? To make our model, we start with our original data, which had a mean of 4.6, then subtract 0.6 from each data point to get a new model. Then we'd simulate taking 1,000 samples of size 28 from this model and get a new simulated sampling distribution. Here is a dot plot showing the distribution of mean weights. Now, what we need to do is find the probability of getting the observed statistic. The observed statistic was 4.6, and this observed statistic is among the 0.4% least likely results, assuming the mean weight is 4.0 ounces. So, the observed statistic is strong evidence that the parameter is not 4.0 ounces. Let's try another parameter value, this time of 4.3. We'll skip over the simulation and look at the resulting sampling distribution. Here is a dot plot showing the distribution of mean weights. Now, what we need to do is find the probability of getting the observed statistic. The observed statistic was 4.6, and this observed statistic is among the 14.4% least likely results, assuming the mean weight is 4.3 ounces. So the observed statistic is not evidence against the hypothesis. Let's try another parameter value of 4.2. Here is a dot plot showing the distribution of mean weights. Now, what we need to do is find the probability of getting the observed statistic. The observed statistic was 4.6, and this observed statistic is among the 5.1% least likely results, assuming the mean weight is 4.2 ounces. And if we're using a criterion of 5%, then this is almost, but not quite, strong evidence against our hypothesis. Now, let's summarize what we've seen here. We weighed 28 scoops of ice cream and got a mean of 4.6 ounces. And we wanted to know, what is the mean weight of all scoops? This mean weight is our parameter. So we thought about our observed statistic of 4.6 ounces. Then we hypothesized that the parameter was 3.5 ounces, simulated repeating our study 1,000 times, and found that the observed statistic would occur in the sampling distribution with less than 5% probability. This was also the case for a parameter of 4 ounces. When we hypothesized that the parameter was 4.3 ounces, we found that the observed statistic would occur with greater than 5% probability. And a parameter of 4.2 ounces seemed to be the smallest parameter value for which this would be true. So this would be true of any parameter value between 4.2 and 4.6 ounces. Now, 4.2 is 4/10 of an ounce less than 4.6. So if we went 4/10 above 4.6, all of these parameter values should also produce the observed statistic with greater than 5% probability. So overall, if the parameter was any value between 4.2 and 5.0 ounces, then the observed statistic would occur with greater than 5% probability. As before, this range of values is called an interval estimate for the parameter. And in particular, since we were using 5% as our criterion for whether the parameter would produce the statistic, it is also called a 95% confidence interval for the parameter. And the method we used for this quantitative variable was essentially the same as the method we used when we were working with a categorical variable.